Thank you very much. To begin with, the title of this presentation is somewhat ambiguous because the radon in the title could refer to two different things. Usually, and as this has been the case in the presentations that we've heard so far this morning, radon refers to the isotope radon-222. But it could also just be the chemical element radon. And in this talk, we'll actually be doing both. So we're looking at the impact of thoron on measurements of the isotope of radon that's normally called radon. We're also looking at general risk assessment due to the chemical element of radon. But for clarity, whenever I'm talking about radon, it will be radon-222, and I'll refer to thoron as thoron to avoid further confusion. And how do I get this to the next slide?
If you click on the presentation,
yeah.
Right?
This one?
Oh, previous one. Yeah. It's a very brief refresher of what radon and thoron are and what the similarities and the differences are. Because I'm aware radon norm is a very broad consortium, and this for many of you this will be familiar, but possibly not for everyone. And both radon and thoron are naturally occurring isotopes of the same noble gas. They're both gases, and their progeny are solid radioactive materials, some of which are alpha emitters, which can cause, well, as we've seen this morning, lung cancer and possibly had other health effects. So that's the most important similarity. The big difference is that radon has a half-life of almost 4 days, and thoron, the half-life is just under a minute. And that will, as a consequence of that, their behavior in the indoor environment, but also their impact on risk, are very different. And historically, the relevance of thoron is usually assumed to be pretty much negligible due to this short half-life, which limits the possibilities for thoron to enter the living environment. It also means that the sources of radon and thoron in indoor air are very different, particularly in high radon areas, and I'm not from one of those, but in high radon areas, the primary source of radon will be the soil, and radon will enter the indoor living space through, for example, basements or crawl spaces, with a contribution from building materials as well. But for thoron, due to the short half-life, it will never manage to escape from the soil, then diffuse through a basement or crawl space, and then enter the living space. It will have decayed long before that. So the only sources of thoron will be finishing materials, and only about 1 centimeters the outer layers of indoor walls or ceilings or floors. And this has important consequences for when trying to assess thoron concentrations, because in high radon concentrations, the dominant factor, the dominant source will be geological, and that doesn't change on very small distance scales, whereas finishing materials can be different from one house to the next, or even from one room to the next. So where, for example, in some of the studies we've seen, estimates for radon concentrations are largely based on the geographical location. That doesn't work for thoron. And what you see in the graph below is that if you look at the thickness of a, for example, a wall, then the amount of radon that can escape from this wall continues to increase if we increase the thickness of the wall up to the thickness of about 1 meter, whereas for thoron, it stops at about 1 centimeter. And the exhalation rates for thoron typically are about a factor 100 higher than the typical ones for radon. This reflects the difference in half-lives. So much for the refresher. Now, what we were doing in radon norm, and this was a task originally led by James Marsh from the UK Health and Safety Authority, who unfortunately had to retire for health reasons, was we were looking at the uncertainties in radon risk assessment due to the presence of thoron. And the important fact that we'll address in the first half of this talk is that some radon detectors that are commonly used in surveys of radon are also sensitive to thoron. And that wouldn't be a problem if the dose per becquerel per meter cubed was the same for both isotopes, and if the sensitivity of the detectors was the same. And the third point, it also wouldn't be a problem if the equilibrium equivalent thoron concentration was well defined. Now, this one is really only relevant if you're looking at health risks due to both isotopes. If you're really only interested in radon, it's primarily the first two. But if you're looking at a public health assessment, then you actually need to have all. Now, why is this relevant for radiation protection? And this is a somewhat older example from the Netherlands, which some of you may wonder why we bother with radon at all, because concentrations are very low. But this shows that the results of two different surveys conducted actually in the previous century, where we were looking at radon concentrations as a function of the year of construction. And as you can see in the blue lines, the median radon concentration, and what you're seeing here is a median and a 5-year running median, increased with year of construction, and then in the latest decades of the previous century, that sort of leveled out. And to ensure that there was no further increase in radon levels, the institute I work for regularly conducted surveys just to see how this was developing. So we did one about 20 years ago, and to our surprise, we suddenly found a dramatic reduction in radon concentrations. And it took, we studied several possible explanations for this, and most of those were related to the fact that between the red survey, and the green, we changed the detector. And in the end, we found out that a large fraction of this apparent decrease probably was due to the fact that in the older surveys, the detectors we had used were sensitive to thoron, and in the new one, the detector we used was not. So in the low radon setting of the Netherlands, this thoron sensitivity of the detector had a huge consequence on our assessment of the presence of radon in houses. And it had a further consequence because it meant that all of our assessments of radon in existing surveys were now suddenly uncertain. Because we did not, even if the manufacturer could give us an indication of the sensitivity of the detector to radon, we still missed a lot of information to reconstruct what the to thoron. We missed important information to reconstruct the thoron contribution, because what we did not know was where the detectors had been placed. And if you look at the graph on this picture, in red, this shows results from detectors placed close to a wall that we knew contained thoron in the finishing materials. In red, we see the results from the old detectors, and in blue, the new one. And as you can see, the thoron contribution, because that's a decreasing one, decreases very, very rapidly with distance to the source. So if you don't know where the detector was placed, you can't reconstruct what the thoron contribution was. And in addition, we also didn't know what the exhalation rates were. So we had no way of reconstructing our radon concentrations in our earlier surveys. And this is not exclusive for low radon areas, because in a study in China with higher radiation, but in dwellings where the walls were finished with soil, a similar effect occurred. But here, the radon concentrations originally reported were in the order of 300 becquerels per meter cubed, and after correcting for a thoron contribution, they were reduced by about a factor of 3 to 100. So there are two settings where this can be important, and that's if you're looking at low radon, where even a small contribution of thoron can thoroughly distort your results, or if you're looking at a situation where your finishing materials contain large quantities of thoron. So this is one of the sustainable development goals where this is relevant, and this may be a bit of a surprise, is the sustainable communities and cities. One of the aspects considered here is the sustainable use of building materials. And some building materials used that are seen as more sustainable actually contain more thoron. This is in particularly true for loam. So as we're moving to more sustainable ways of building, this problem might become more important. Okay, so this is, so we have the radon detectors that might be sensitive to thoron as well. This is also relevant for climate action, because if we're now, it was briefly mentioned that this morning that in the radon showcase meeting, the European Union expressed an interest in relations between energy efficiency and radon concentrations. If we're making our houses more energy efficient and changing the ventilation, this will change the presence of radon in houses, but also that of thoron. So if we want to obtain a thorough understanding of the effects of energy retrofitting, we should actually understand both. what happened here? Okay, so just a very brief explanation of why detectors can be sensitive to thoron. So your typical passive radon detector used in many surveys, and there are more, but this is just an explanation for the typical passive one, is a plastic container containing a small piece of transparent plastic, CR39, and radon gas diffuses into the detector and eventually decays in proximity of this piece of plastic, which leaves tracks in the plastic which can be counted. But if radon can diffuse in, so can thoron. And if the diffusion distance to the actual detector is short, thoron can reach this detector before it decays. This also points in what you can do to make detectors more selective for radon. If the typical diffusion time is of the order of 10 minutes, so 10 times the half-life of thoron, the thoron contribution will be very limited. Another measure you could take is position detectors away from any possible sources of thoron, so at least about 50 centimeters. And in large-scale surveys, this second method would be less reliable because it's harder to control what people will do once the detector has been placed. And we found that in many cases people tend to move them, so even if you initially place them at 50 centimeters, they may not stay there. To assess the effect of thoron on radon surveys and also epidemiological studies, we conducted a survey in radon, and the motivation for this was primarily that if concentrations that are overestimated, because part of the reported concentration of radon is actually thoron, that might lead to an underestimate of radon risk in epi studies. So we distributed a questionnaire on thoron sensitivity of detectors used in studies, the position of the detectors, smoking behavior, and further relevant aspects of the study protocols, and received a very limited response from Italy, Switzerland, South Korea, and India, with a possible bias, because if we look at who responded to this survey, the people who tended to be aware of the issue. So these are primarily people who are very much aware of possible thoron consequences, who already dealt with it, and people who are not so much aware of it didn't reply, with the exception possibly of Switzerland, where the Ben Speaker, who talked about his study this morning, did actually report, and there are some indications, and this is by no means a criticism of the study, but that some of the detectors used in that study may in fact have been sensitive to thoron, and there's no way of determining if that had any effect on the dosimetry, although given the other large uncertainties, it's likely to be limited, but we can't quantify it. We could try much harder to complete this questionnaire, but there's actually, we may question the usefulness of that, because it's very hard to, even if we did know which detectors were used, that would still make it very difficult to then go back and reconstruct the actual radon concentrations in studies where detectors were used that were also sensitive to thoron. Because you'd need knowledge of the actual sensitivity to thoron, so if 1 becquerel of thoron is measured, how is that reported? You need to have information about the detector position and about the thoron exhalation rate. And in general, that information will not be available. In the case of the Chinese study, where the dramatic corrections of radon rates were made, this information was available because those houses were fairly uniform. So there was information about the finishing materials used, and there was also detailed information about the placement of detectors. However, for example, in our Dutch survey, we had no way of doing this reconstruction, and that is likely the case for many of these studies. Okay, I'm rapidly running out of time. So, I'm going to skip the second part of this, which was more about if we now also want to assess the effect of thoron on health, then ideally, if you wanted to do this in a way analogous to radon, you would like to have knowledge of the equilibrium factor. So for radon, you measure radon, multiply by an equilibrium factor to obtain the equilibrium equivalent concentration, and from this you obtain a dose. Now, for thoron, this will not work, because there is no such thing as an equilibrium equivalent concentration, but you can still meaningfully define an equilibrium equivalent concentration. This now no longer has the meaning of of an ideal mixture of thoron in equilibrium with the daughters, because due to the half-lives that won't exist, but you can define it. However, if you're now measuring thoron and try to relate this to this equilibrium equivalent factor, you run into problems. And that's shown in this graph, and this is pretty much the last thing I'll show. On the left axis, you see the ratio between the equilibrium equivalent radon concentration and the measured radon concentration as a function of the distance to a nearest wall. On the right, you see the same for thoron. And the dotted line gives its ratio for radon. It's constant, usually taken about 1.4 by RCRP. For thoron, as you can see, it increases rapidly with distance to a wall, meaning that the equilibrium factor is ill-defined. And there are sources in the literature that do define an equilibrium factor, but I would strongly advise against this, because it depends very much on where you are looking. So how to get around this? Well, rather than measuring thoron and trying to relate that to an equilibrium equivalent concentration, it might be better to measure the thoron progeny, which actually causes the health effects. And fortunately, that is possible. Well, it's beyond the task that we were looking at here, but if you use the specific characteristics and the very high energy of one of the thoron progeny, it actually is feasible to, rather than measure thoron, measure the progeny, which avoids this whole problem of having to find an equilibrium factor. So it doesn't exist, but we also don't need it. So to summarize, some detectors that are routinely used in surveys are sensitive to thoron. It's very hard to correct for this afterwards. So the take-home message is, if you're going to do measurements, ensure that your detector is not sensitive to thoron before you start. If you want to do a full assessment of public health related to exposure to the chemical element radon, then make sure you measure thoron, or rather thoron progeny as well. Thank you very much for your attention.